Hey there, and welcome. Today, we're tackling one of the biggest, most important ideas in all of chemistry. It's a tool that lets scientists count things that are, well, completely invisible. So, how in the world do they do it? Let's get into it. So, picture this. You're a chemist, right? And your recipe doesn't ask for a cup of this or a teaspoon of that. Nope. It calls for a very specific number of atoms. How do you even begin to measure that out? This was the exact problem that had scientists scratching their heads for a long, long time. I mean, just stop and think about that for a second. There are more atoms in one little grain of sand than there are grains of sand on every beach on the entire planet. Counting them one by one? Yeah, that's not going to happen. So chemists needed a clever workaround. They needed a shortcut. And that brilliant shortcut is something called the mole. Now, the best way to wrap your head around it is to think of it as a chemist's dozen. A baker doesn't ask for 12 eggs, they just say, give me a dozen. It's just a convenient word for a specific number. Well, for chemists, the mole is the exact same thing, it's just a word for a number. A very, very, very big number. And that magic number, it has a name, Avogadro's number. This is the specific number of particles, we're talking atoms or molecules, that you'll find in 1 mole of anything. Doesn't matter if it's a mole of iron, a mole of water, or a mole of sugar, the number of tiny little particles inside is always the same. And here it is in all its glory, 6.023 times 10 to the 23rd power. That's a 6 with 23 zeros tacked onto the end of it. It is an unbelievably huge number. If you had a mole of pennies, you could give every single person on Earth a stack of them that reaches the moon over 1,000 times. It's a number so big it's hard to imagine, and it's the key to everything we're about to do. Okay, so a mole is a number. Got it. But that's still pretty abstract, right? How do we actually use that in a real lab? Well, this brings us to the first tool in our chemist's toolbox, connecting that giant number to something we can actually measure, its weight. This is the million-dollar question. If I say a dozen eggs, you can picture it. You know what it feels like. But what does 1 mole of, say, water actually look like? How much does it weigh? Thankfully, there is a surprisingly simple way to figure that out. We can figure this out using a tool that every chemist has on their wall, the periodic table. Let's use water, H2O, as our example. So we've got 2 hydrogen atoms and 1 oxygen atom. All we have to do is look up their atomic masses on the table, multiply by how many of each we have, and then just add it all together. For water, that's 2 times the mass of hydrogen, which is about 1, plus 1 times the mass of oxygen, which is 16. And that gives us 18. And here is the really cool part. That number, 18, is exactly how many grams 1 mole of water weighs. 18 grams. That's an amount you can easily measure out on a scale. See what we just did? We just built a bridge from an impossibly huge number of invisible molecules to a real, tangible weight. All right, so now we know how to find the weight of 1 mole of something. This is where the mole really starts to show off and becomes the ultimate tool for a chemist. Think of it like a central hub or a translator that lets us easily convert between 3 super important measurements: mass, volume, and the actual number of particles. Let's see how it works. Okay, let's try our first conversion. Imagine you're in the lab and you've got 46 grams of sodium sitting on a scale. The question is, how many moles is that? The formula for this is just so simple. It's beautiful. You just take the mass you measured, 46 grams in this case, and you divide it by the atomic mass of sodium, which you can just look up on the periodic table. It's 23. Do the math, and you get 2 moles. We have exactly 2 moles of sodium. Easy as that. So what about gases? We don't usually weigh gases. We measure their volume. So new question, how many moles are in 5.6 liters of oxygen? Now for this to work, we need to make sure we're comparing apples to apples. So chemists came up with something called standard temperature and pressure, or STP. You can just think of it as a set of standard baseline conditions, so all the measurements are fair. Here's the handy trick. At STP, 1 mole of any gas always takes up the exact same amount of space, 22.4 liters. We call this the molar volume. So to find our answer, we just take the volume we have, 5.6 liters, and divide it by that magic number, 22.4, and that tells us we have 0.25 moles of oxygen. All right, for our last basic conversion, we're going to go full circle.
What if someone just gives you the raw number of atoms, like, say, 12.046 times 10 to the 23rd atoms of iron, and asks you, how many moles is that?
Well, we just bring back our friend Avogadro's number. We take that huge number of atoms they gave us, and we simply divide it by Avogadro's number. And you might notice that 12.046 is just exactly double 6.023. So the math is super simple. It's exactly 2 moles of iron.
So there you have it. We've got our 3 basic conversions: from mass, from volume, and from the number of particles. Now the really fun part is when we start combining these tools to solve more interesting multi-step chemistry puzzles. Let's put our skills to the test with a classic chemistry problem. Let's say we have 54 grams of water. The question isn't how many moles, it's how many actual individual molecules are in there. This is where we need to use more than one tool from our toolbox. Okay, step 1. Before we can figure out the number of molecules, we first have to get to our central hub, which is moles. So we use our mass conversion tool. We take the mass we have, 54 grams, and divide it by the molecular mass of water, which we already figured out is 18, and that gives us 3 moles of water. Great. Now that we know we have 3 moles, we can pull out our second tool. We know that 1 mole has Avogadro's number of molecules. So it makes sense that 3 moles would have 3 times that amount, right? So we just multiply our 3 moles by Avogadro's number. And voila, there's our answer. In just 54 little grams of water, there are 18.069 times 10 to the 23rd molecules. By putting 2 of our simple tools together, we've solved a much bigger problem. We've successfully counted the uncountable. Okay, we've been doing some math, but let's zoom out for a second. Why is this so incredibly important? Why does every single person who studies chemistry have to learn this? It's because the mole isn't just a number or a tool. It's the fundamental language of chemistry itself. So let's wrap this all up. The mole started as a simple concept, right? A chemist's dozen for counting atoms. But its real genius is that it's the bridge that connects the invisible world of atoms and molecules to the very real, measurable world of grams and liters that we use in a lab. And it's that bridge that lets us write and follow chemical recipes with absolute precision, turning chemistry from just mixing stuff together into a true predictive science. By getting a handle on the mole, you've really unlocked a new way of seeing the world around you. You now understand the basic language that allows us to design new medicines, create new materials, pretty much everything. It all starts with being able to count the invisible. So the only question left is, now that you know how, what do you want to build?